Before we step into the heart of this story, let me ask you something. What if the world you move through every day is not behaving the way your senses insist it is? What if falling is not a pull, but a quiet surrender to a path carved into the fabric beneath your feet? If time can stretch and slow in the presence of mass, then what does that say about the moments you believe are steady and unchanging? And if the space around you can curve so subtly that you never notice it, how many of your most familiar experiences might be illusions shaped by a deeper geometry? From the moment you wake and feel your body press against the ground, gravity seems simple. It feels like a downward force, steady and familiar, shaping every motion without ever revealing its true nature. You drop a stone and it falls. You jump and you return to the earth as if an invisible hand pulls you back. Your senses insist on this story because the experience is so immediate and so constant that questioning it feels almost unnatural. Yet the universe does not owe its truth to our intuition, and history shows that our instincts often misunderstand the workings of nature. The world feels flat until you learn it curves. The air feels empty until you discover it carries pressure. The sun seems to travel across the sky until you realize you are the one moving. For centuries, Newton's idea of gravity acted as a lighthouse for the scientific world. He described gravity not as a mystery, but as a simple attraction between masses, an idea powerful enough to explain the motion of planets, the tides sculpted by the moon, and the falling of an apple from a branch. His mathematics guided sailors, astronomers, and engineers with extraordinary precision. The planets followed predictable paths. Comets returned on schedule. The moon pulled on the oceans exactly as calculated. It was a triumph of human understanding. Yet even Newton himself admitted that he did not know what gravity really was. He could describe its effects, measure its strength, and predict its consequences, but he offered no mechanism for how a mass could exert influence across empty space. This unanswered question grew heavier as scientists uncovered deeper laws of nature. When experiments revealed that nothing can carry information faster than the speed of light, Newton's picture of instant gravitational influence began to show cracks. If the sun were to vanish at this moment, Newton's model said the Earth would feel the loss instantly. But physics demanded that changes cannot propagate faster than light. The contradiction was impossible to ignore. If space and time obey strict limits, then gravity must obey them as well. Something about the old picture no longer fit the increasingly precise understanding of the natural world. Astronomers began to notice that even Newton's extraordinary equations could not explain everything. Mercury, the innermost planet, traced a path that shifted in a way Newton's laws could not fully account for. The amount was small, but undeniable. It was as if the fabric guiding Mercury's orbit carried a wrinkle that no classical calculation could smooth out. The more precisely scientists observed the heavens, the clearer it became that the universe was whispering hints of a deeper truth. The old framework worked beautifully for most situations, yet it failed at the edges where nature revealed its more delicate structures. As 19th century science matured, the tension between the old and the emerging grew sharper. Electromagnetism presented a universe where light and energy respected strict speed limits, while Newtonian gravity seemed to ignore them completely. Precision instruments exposed tiny discrepancies in planetary motion, each one a quiet reminder that the classical model was incomplete. Nature was not breaking its own rules. Humanity was simply missing a piece of the picture. Into this landscape of unanswered questions stepped Einstein, a man who looked at familiar ideas with uncommon clarity. He realized the problem was not with the planets or the measurements or the mathematics. The problem was with the assumptions about space and time themselves. For centuries, scientists treated space as a flat stage and time as a universal rhythm, steady and absolute. Einstein asked a different question. What if the stage could bend? What if the rhythm could change? What if gravity was not a force acting through empty space, but a sign that space and time were not rigid at all? This idea was more than a shift. It was a transformation, one that required letting go of centuries of intuition. Instead of thinking of gravity as a pull, Einstein imagined it as the natural motion of objects following the shape of curved spacetime. What we feel as weight is not the Earth pulling us downward, it is the ground pushing upward against our natural path. What we see as a planet orbiting is not the sun tugging it around, but the planet following the curve carved by the sun's mass. Yet this was not fantasy. It was a logical consequence of the rules physics had already established. Light has a universal speed. Space and time are intertwined. Motion depends on the observer. Each idea pointed toward a universe that behaves not through invisible forces, but through geometry. A geometry so subtle that everyday experience cannot reveal it. The need for a new understanding of gravity was not born from imagination, but from evidence pressing from all sides. The classical picture succeeded spectacularly, where conditions were gentle, but the cosmos is not always gentle. When masses grow large or speeds approach the speed of light, the old rules bend until they break. The universe demanded a theory capable of honoring its limits, respecting the speed of light, matching precision observations, and explaining the mysteries that Newton's model left untouched. Einstein's insight was not that Newton was wrong, but that Newton was describing only the surface of a much deeper truth. What he uncovered would reshape every corner of physics. But before we follow him into that revolution, we must step back into the world he inherited, a world where space was fixed, time was absolute, and gravity was a force acting across emptiness. That world is where our story truly begins. The picture of the old universe lingers for a moment, quiet and ordered, built on the certainty that space is a vast emptiness, and time is a single heartbeat shared by all things. It is a comforting vision, one that lets you believe the cosmos behaves like a grand clock, where every gear turns in perfect rhythm. Yet as you let that image settle, you can sense something unsettling beneath its surface, something waiting to be noticed. The planets move with elegance, but their paths contain tiny irregularities. Light rushes across space with a speed no force can overtake, yet gravity in the classical world seems to leap across distance without delay. These contradictions drift through the 19th century like faint echoes of a truth not yet understood. Scientists who mapped the heavens felt these echoes long before they could explain them. They watched Mercury carve its looping path around the Sun, and noticed that the point of its closest approach drifted slightly more than Newton's equations predicted. The difference was small, a sliver measured across decades, yet it was persistent and real. Each precise measurement confirmed that something deeper was shaping the orbit. Astronomers tried to save the old model by proposing unseen planets or hidden masses, but every attempt faded under scrutiny. Nature was whispering that the classical picture, though powerful, did not reveal the full shape of reality. Meanwhile, discoveries in electricity and magnetism began tightening the tension further. Experiments showed that light travels at a fixed speed, the same for every observer, no matter how they move. This fact did not fit comfortably with Newton's idea of absolute time. If time were universal, then speeds should add in simple ways. But light refused to cooperate. It moved as if space and time themselves adjusted to protect its constancy. This was not a minor curiosity. It was a sign that the very structure of physical law was more flexible than scientists had dared to imagine. In laboratories across Europe and America, experiments kept pointing toward a deeper truth. The Michelson-Morley experiment revealed no difference in the speed of light as the Earth moved through space, crushing the idea of an invisible medium that carried light waves. Atomic physics began revealing that time behaved differently for particles traveling at extreme speeds, living longer than they should. Even before Einstein arrived, nature was preparing the ground, laying clues that the old order was cracking. Yet the most profound clue was hidden in plain sight. In Newton's universe, gravity acts instantly. If the sun were to shift its position, the Earth would feel the change immediately. But This idea contradicts the hard limit set by the speed of light. Nothing, not even a hint of information, can travel faster than that cosmic limit. So how could gravity be instantaneous? This contradiction gnawed at the edges of classical physics, like a quiet but relentless tide. Scientists understood the problem, yet they had no framework to resolve it. Space was supposed to be empty. Time was supposed to be absolute. Gravity was supposed to be a force reaching across the void. If any of these assumptions were wrong, the entire worldview would need to be rebuilt from its foundation. Into this growing uncertainty stepped a young man with a way of thinking that drifted outside the familiar boundaries. Einstein did not begin with complex instruments or grand observatories. He began with thought, with imagination shaped by reason, asking questions so simple that they became profound. What would the world look like if you could ride alongside a beam of light? How would a clock behave in a fast-moving frame? If a person fell freely in a sealed room, what would they feel? These questions were not whimsical. They were the first threads of a new tapestry that would redefine the universe. Einstein sensed that the trouble lay not with the planets, nor with the equations, nor with the measurements. The trouble lay with the assumptions that had gone unquestioned for centuries. What if space was not empty and fixed, but something that could shift and stretch? What if time was not a universal rhythm, but a phenomenon that could tick differently depending on motion and gravity? What if gravity was not a force at all, but simply the natural path objects follow when the fabric of space-time curves around mass? These ideas did not emerge in a single moment. They formed as Einstein wrestled with contradictions that other scientists had grown accustomed to ignoring. He realized that the universe does not bow to human intuition. It obeys principles woven into the structure of space-time, principles that cannot be forced into anyone's expectations. As the pieces aligned, a new picture began to form, one where gravity needed no mysterious pull and no action across a distance. Instead, mass would shape the geometry of space-time, and objects would move along that geometry naturally, as water flows along the curve of a valley. The old world, with its certainty and simplicity, began to fade. In its place rose a universe more subtle, more intricate, and far more beautiful. A universe where falling becomes a revelation about the shape of space-time itself, and where every orbit, every beam of light, every moment of time reflects a deeper structure waiting to be understood. The old picture of gravity, held together by centuries of success, now stands like a monument whose foundation has quietly begun to shift. You can almost feel the weight of those unresolved contradictions pressing against it, the way a structure strains long before it finally yields. Scientists of the late 19th century were experts in measurement, carefully charting the heavens with instruments of rising precision. Each new observation brought more clarity to the sky and more tension to the theory supposed to explain it. Mercury continued its slow drift, a gentle but persistent reminder that something in the cosmic design did not align with Newton's expectations. The speed of light refused to behave as a simple additive quantity, suggesting that the very language of motion needed revision. And through it all, the idea of instantaneous gravity sat like a quiet paradox, untouched, yet impossible to ignore. As these pieces gathered, the world found itself standing at the edge of an unseen transformation. Humanity had spent generations accepting the classical framework of space and time, trusting that the universe was straightforward if only one looked carefully enough. But the deeper physicists looked, the more the universe hinted at hidden layers. Time did not seem to pass at the same rate for fast-moving particles. Light behaved as though it followed strict rules that no familiar force could command. Even the concept of distance appeared less fixed than once imagined, shifting subtly with the observer's motion. The natural world was gently outlining a truth more intricate than the one people had grown comfortable with. Einstein climbed into this unfolding landscape with a perspective shaped not by advanced age, or academic authority, but by relentless curiosity. He believed that nature should be simple at its core, even if the appearance seemed complex. When contradictions appeared, he did not dismiss them or try to force them into the old mold. Instead, he questioned the mold itself. He imagined clocks ticking differently depending on how they moved. He imagined space contracting when viewed from different frames. He imagined gravity not as something imposed from afar, but as something emerging from the shape of space-time. These were not fantasies. Each idea was grounded in the evidence already gathered, evidence that demanded a new interpretation. Imagine standing on the surface of the Earth, feeling your weight press against the ground. The classical view tells you that the Earth is pulling you downward, but Einstein realized that this sense of weight is not a pull at all. It is the ground pushing upward on you, resisting the natural path that space-time has laid before you. If the ground were removed and you were allowed to fall freely, the feeling of weight would vanish. This disappearance is not because gravity has weakened, but because you are now moving along the natural curve of space-time without obstruction. This simple insight, born from imagining an elevator in free fall, became the seed of a theory that would rewrite the structure of physics. The brilliance of this idea lies in how naturally it resolves the contradictions that haunted the classical model. If gravity is a feature of space-time geometry, then changes in gravitational influence do not need to travel instantly. They move as quickly as distortions in space-time can propagate, which is the speed of light. This preserves the fundamental limit revealed by electromagnetism. It explains why Mercury moves the way it does, tracing its orbit along a curved space-time shaped by the intense gravity near the Sun. It clarifies why light bends as it passes near massive objects, not because it is being pulled, but because it is following the shortest path available in a curved environment. Suddenly, the universe becomes coherent again. Every mystery that once seemed disconnected aligns into a single narrative. This shift did more than fix broken pieces. It opened a door into a new way of seeing the cosmos. Gravity became a story of geometry, mass became a sculptor of space-time, and motion became a response to curvature rather than force. The universe transformed from a stage where objects acted upon one another to a dynamic fabric where the shape of space and the flow of time guide every step. It is a revelation that seems almost poetic, yet it is rooted firmly in measurement, observation, and mathematical truth. As you let this new picture settle in your mind, the old world feels distant. The notion of gravity as a simple pull fades like an echo from an earlier age. What rises in its place is a universe alive with structure, where space can stretch and bend, and time can slow and shift. Einstein did not replace mystery with certainty. He replaced one mystery with a deeper one, a mystery that invites exploration while remaining grounded in evidence. And this is where the journey truly begins, because to understand how Einstein reshaped our vision of gravity, we must step fully into the universe he challenged. For a moment, imagine stepping back into the world before Einstein, a world illuminated by candlelight observatories and guided by equations that seem to decode the heavens with flawless precision. In this era, the universe felt like a grand machine, steady and predictable, built on rules that appeared complete. Newton's laws did not just describe nature, they shaped humanity's confidence in its ability to understand nature. They offered a universe where every motion could be traced, every orbit calculated, and every falling apple explained through a single elegant idea. Gravity, in this classical picture, was a mutual attraction between masses, a simple pull acting across space, and it seemed to work everywhere one looked. This vision was so successful and so intuitively comforting that it became woven into the fabric of everyday thinking. You felt your weight and believed the Earth was pulling you downward. You watched the moon rise and assumed the Earth was keeping it in place through an invisible Ships navigated the oceans with charts based on Newton's mathematics. Astronomers plotted the paths of planets and predicted eclipses with astonishing accuracy. The certainty was intoxicating. It created the sense that the cosmic order had been fully mapped, leaving nothing but minor details for future scientists to polish. Yet even within this triumphant picture, there were mysteries that refused to fit. One of the earliest signs came from the idea of absolute space and absolute time. Newton imagined that space was a vast, unchanging stage, eternally fixed, independent of anything placed upon it. Time, he believed, flowed in perfect uniformity everywhere in the universe. These assumptions were not proven. They were accepted because they made the mathematics work, and because they matched the intuition of people who lived at human scales, where the limits of physics rarely show themselves. For centuries, nobody questioned these foundations because everything they touched seemed to confirm them. But the universe is far larger and far stranger than intuition suggests. As astronomical measurements became more precise, tiny cracks appeared beneath the smooth surface of Newton's masterpiece. The most famous of these cracks traced back to Mercury, the innermost planet. Its orbit did not behave exactly as predicted. The point where it made its closest approach to the Sun drifted slightly more than Newton's equations allowed. The difference was small, but it persisted through every improved observation. It was a quiet distortion, as if the fabric guiding the planet carried an unseen twist. This anomaly lingered for decades, resisting every attempt to preserve the classical explanation. Scientists proposed hidden causes, hoping to keep the old framework intact. Some suggested an unseen planet closer to the Sun, a world that might nudge Mercury's orbit in just the right way. Others adjusted the distribution of matter in the solar system, searching for any arrangement that could fit the data. But each new idea collapsed under scrutiny. The anomaly remained, a stubborn reminder that the classical world might not be the final word. Meanwhile, discoveries unfolding on Earth added tension to the cosmic puzzle. Experiments with electricity and magnetism revealed patterns that resisted the simplicity of Newtonian thinking. Light behaved as if it obeyed a universal speed limit, refusing to bend to the classical rules of motion. If you moved toward a beam of light or away from it, the speed you measured stayed the same. This was not a matter of imprecise equipment. It was a fundamental feature of nature, one that clashed with the idea of absolute time. If time were universal, the speed of light should vary based on your motion. But it did not. It remained fixed, as if nature were guarding a deeper truth. The Michelson-Morley experiment sharpened this contradiction into something undeniable. As Earth orbited the Sun, the speed of light did not shift at all, not even by a whisper. This result forced physicists to confront the possibility that space was not the passive emptiness they imagined. Something more subtle was happening, something that could not be explained by a rigid universe governed by instantaneous forces. And through it all, the question of gravity's speed lingered like a shadow. According to Newton, if the Sun were to move or vanish, the Earth would feel the change immediately. But this idea violated the growing evidence that nothing can propagate faster than light. If gravity were instantaneous, it would break the very principles that underpinned electromagnetic theory. The contradiction was stark and inescapable. Either gravity behaved differently from every other influence in the universe, or the classical picture needed to be rebuilt from its foundation. Despite these problems, Newton's theory remained astonishingly successful in most situations. Its predictions matched experience whenever gravitational fields were gentle and speeds were much slower than the speed of light. Engineers relied on it. Astronomers trusted it. It remained indispensable for building bridges, guiding cannons, and plotting planetary paths. But the universe is not obligated to match human convenience. Where masses grow extreme or speeds approach their upper limit, the cracks in the classical model widen into chasms. You can feel this tension as a kind of quiet pressure in the narrative, the sense that a magnificent structure is carrying a hidden flaw. Newton's universe is elegant, consistent, and powerful, yet incomplete. It works beautifully within its domain, but its edges reveal the need for something deeper, something that can explain Mercury's drift, respect the fixed speed of light, and avoid instantaneous influence across the void. The stage is set. The classical world is beginning to wobble, and into that instability walks Einstein, ready to question the assumptions that everyone else accepted as beyond question. The classical universe now stretches before you like an immense and perfectly drawn map, its lines crisp and its logic certain, yet you can sense that something beneath its surface is shifting. The confidence that once surrounded Newton's picture begins to feel like a calm sea hiding deep, unseen currents. Scientists of the late 19th century stood in this moment without realizing how close they were to a transformation. They trusted a framework that had guided humanity for centuries, a framework that made the heavens predictable and the earth comprehensible. Yet each new discovery pressed gently but persistently against that confidence, like soft fingers tapping on a locked door. Mercury's orbit continued to whisper that something was missing. No matter how carefully astronomers observed, the planet insisted on carving a path that did not match the classical predictions. It moved through a gravitational landscape that Newton could describe in broad strokes, but not with perfect accuracy. The discrepancy was not large enough to overthrow the theory, yet it was too real to ignore. It was the kind of clue that waits patiently for the right mind to notice its deeper meaning. At the same time, the behavior of light carved open cracks in the assumptions of absolute space and absolute time. Physicists discovered that light does not care how fast you move toward it or away from it. It greets every observer with the same speed, as if it carries its own rulebook that nothing else can override. If you stand still or race forward, the number you measure remains unchanged. This cannot happen in a universe where time ticks alike everywhere, and space remains rigid for all observers. It can only happen in a world where the rhythm of time adjusts itself depending on motion, and where space quietly reshapes to accommodate that change. These discoveries did not belong to Einstein alone. They emerged from laboratories and observatories across the world. They were uncovered through careful measurement, not speculation. The Michelson-Morley experiment, repeated with ever-increasing precision, confirmed that light refuses to vary its speed in the slightest. The more physicists tried to catch nature contradicting itself, the more nature held firm. Something fundamental was being revealed, something that refused to fit inside the classical framework. Meanwhile, new insights into electricity and magnetism brought another blow to the classical picture. Maxwell had shown that light is a wave of electromagnetic fields, and his equations described how these fields move through space. But these equations predicted that light must travel at a specific speed, a speed that seemed woven into the fabric of reality itself. If light were to obey Newtonian ideas of absolute time, its behavior would not align with these equations. And yet it did. Every experiment confirmed Maxwell, not Newton, when it came to the nature of light. The tension grew deeper when scientists examined how forces behave across distance. Electromagnetic forces do not act instantly. They ripple outward at the speed of light, carrying influence only as quickly as the universe allows. This limit is not optional. It is a cornerstone of physical law. But Newton's version of gravity appeared to ignore it entirely. If the sun were to move, the Earth in the classical picture would feel that change immediately. This is not just unlikely. It is impossible within the rules established by electromagnetism. Something fundamental was broken in the old model, even if the cracks were visible only to those who looked closely. Yet the classical framework did not collapse. It remained powerful and reliable in most contexts. Engineers building bridges, astronomers plotting eclipses, and navigators charting the seas had no reason to abandon it. Newton's equations continued to function with stunning accuracy whenever gravitational fields were moderate and speeds were far below the speed of light. The problem was not that the classical theory was wrong. The problem was that it was incomplete. It described the surface of reality, but not its depths. The deeper truth was waiting in the shadows of these contradictions. A universe that respects the speed of light cannot allow instantaneous gravity. A universe that shows time stretching for fast-moving particles cannot maintain a single universal rhythm. A universe where space bends under the influence of electromagnetic fields cannot remain perfectly rigid under all conditions. Something more flexible, more dynamic, and more interconnected must underlie the motions we observe. As these clues gathered, the classical model began to resemble a beautiful painting that had been admired for generations, but now needed restoration. The colors were fading at the edges, and hidden details were emerging beneath the surface. It would take a new perspective to understand these details, a willingness to question foundations so deeply accepted that they had become invisible. Einstein was that perspective. He approached the contradictions not with the intention to break the classical world, but with a desire to understand why it succeeded and where it failed. He recognized that Newton's laws were not false, but limited, and that the universe was quietly pointing toward a hidden structure more elegant than anyone had imagined. The stage is now set for that revelation. The old universe is holding its breath, and the next step is the moment when time itself loses its absoluteness. The classical universe now feels like a grand clock whose gears turn with perfect predictability, yet each passing discovery reveals that some of those gears are shaped differently than anyone expected. You stand in this world of rising precision, watching scientists measure the cosmos with instruments more sensitive than ever before. Every improvement in technology sharpens the details of the sky, and with that clarity comes a growing unease. The discrepancies once dismissed as noise begin to appear as signals. The tiny drift of Mercury is no longer an error of measurement, but a message from the structure of reality itself. The constant speed of light is no longer a curiosity, but a declaration that the old understanding of space and time cannot be the whole story. Beneath the surface of Newton's universe lies a problem that grows more troubling the longer you stare at it. If light cannot outrun itself, then time must behave differently depending on how one moves. If time can stretch, then distance must also shift to preserve the laws of nature. If space and time can change depending on motion, then the entire concept of absolute space becomes fragile. Each clue contributed by experiment does not stand alone. Instead, they form a pattern that points toward a universe far more fluid than the classical one, a universe that refuses to remain fixed regardless of who observes it. The classical understanding of gravity becomes especially strained under this growing weight. It asks you to believe that masses exert influence across empty space without any delay. It imagines gravity as a silent thread pulling two objects together, regardless of the distance between them. But as physicists examine the behavior of electromagnetic forces, they realize that influence cannot travel infinitely fast. Nature enforces a limit carried by the speed of light. The idea that gravity could break this rule without consequence becomes harder and harder to defend. The classical picture survives only because it works so well in gentle environments, where the weaknesses of the model remain hidden under layers of approximation. But nature is not always gentle. In the intense gravity near the sun, in the high speeds of particles moving close to the speed of light, and in the delicate balance of astronomical measurements, the classical universe begins to strain. It cannot hide its flaws forever. Light bends as it passes near massive bodies, but classical physics cannot fully explain this. Time slows near strong gravitational fields, but classical physics does not predict this at all. Clocks carried on fast-moving aircraft or orbiting satellites do not tick in unison with those on the ground. The universe reveals these truths not through theory, but through experiment, insisting that the old assumptions must change. Scientists felt the tension rising, yet they stood at the edge of a transformation without knowing how to step across it. They could not abandon Newton, because his equations continue to succeed in countless applications. They could not ignore Maxwell because electromagnetic theory was supported by overwhelming evidence. And they could not dismiss the anomalies because each one spoke to a deeper reality. The pieces were all there, scattered across the scientific landscape, waiting for someone to arrange them into a new picture. Einstein entered this scene not as a destroyer of the old order, but as a careful listener to the clues nature had already provided. He sensed that the contradictions between Newton's gravity and the speed of light were not signs of failure, but invitations to understand spacetime in a new way. He realized that the assumption of absolute time was not a law of nature, but a human habit, one that had never been tested in extreme conditions. He recognized that Newton's concept of instantaneous influence was an approximation, not a fundamental truth, and he understood that the universe could remain coherent only if space and time were allowed to adapt themselves to the laws that govern light. In questioning the most deeply rooted assumptions of the classical world, Einstein revealed something remarkable. Space is not a passive emptiness. Time is not a universal rhythm. Gravity is not a pull acting across a void. The universe is a dynamic fabric, bending and shaping itself in response to mass and motion. Newton had mapped the visible surface of this fabric with extraordinary success, but he had not seen the underlying texture. Einstein was the first to imagine the universe in a way that could reconcile every contradiction, preserve every successful prediction of the past, and explain every anomaly discovered across centuries of observation. As the old assumptions fade, you can feel the universe rearranging itself around a new idea. The classical world does not collapse. It transforms, revealing that its truths were approximations built upon a foundation that needed to be deeper. And now that deeper foundation is waiting to be explored, leading to a world where time is flexible, space is curved, and gravity becomes something entirely different from what intuition suggests. Before you take your first step into this chapter, pause for a moment and imagine holding a clock in your hand. Imagine walking with it, running with it, lifting it upward toward the sky. You expect it to tick the same everywhere, beating out identical seconds no matter how you move. But what if that expectation is only a habit of perception? What if time itself behaves more like a living rhythm, stretching or tightening depending on the motion you carry through space? And if time can shift its pace, what does that say about the very fabric that holds the universe together? The world at the dawn of the 20th century did not yet grasp this possibility. Time was treated as a universal flow, steady and unchanging, ticking the same for every observer. Space was imagined as a vast emptiness, rigid and absolute, indifferent to movement or the presence of matter. These ideas had been so deeply trusted for so many centuries that questioning them felt almost unthinkable. Yet the clues had already been laid out across the scientific landscape, waiting for someone brave enough to read them without trying to force them back into the classical mold. Einstein approached these clues with a mind untouched by the constraints that shape traditional thinking. He understood that the strange behavior of light was not a puzzle to be solved through minor adjustments, but a sign that reality itself was structured differently from what anyone had imagined. The fact that light moves at a fixed speed for all observers was not an inconvenience. It was a revelation. If the speed of light remains unchanged, no matter how fast you chase it or flee from it, then the familiar ideas of space and time must bend to accommodate this rule. Nature would not change its fundamental limit. Instead, it would reshape the experience of those who move within it. This realization did not come suddenly. It grew from the evidence. When the Michelson-Morley experiment searched for changes in the speed of light as Earth moved through space, it found none. When physicists studied particles created in the upper atmosphere, they discovered that these particles lived longer when moving close to the speed of light than when at rest. These observations were not contradictions, they were signals. They indicated that time was not behaving as the classical world expected. Time was responding to motion, stretching gently to preserve the cosmic limit that light carries through the universe. Imagine riding alongside a beam of light, watching it flow beside you. It seems impossible, yet asking this question allowed Einstein to see what others had missed. If you could match the speed of light, the beam would appear frozen beside you. But this cannot happen, because light always moves at the same speed relative to any observer, so something else must give way. To preserve the fixed speed of light, the universe must allow time to slow for fast-moving observers. It must allow lengths to contract along the direction of motion. It must allow simultaneity to break apart, so that two events considered simultaneous for one observer may not be simultaneous for another. These adjustments are not tricks or illusions. They are the way the universe maintains its consistency. Time dilation, the slowing of time for fast-moving objects, is not a mere idea but a measured fact. Clocks flown around the world return ticking differently from those left on the ground. Particles traveling close to the speed of light survive far longer than their resting lifetimes. Satellite systems rely on these differences to function correctly. Without accounting for time dilation, every device that depends on precise timing would drift into error, and so the classical picture of time collapses gently under the weight of evidence. Time must be flexible, space must be adaptable. The two must intertwine into a single entity called spacetime, where motion determines how both are experienced. This four-dimensional fabric does not follow human intuition. It follows the laws that govern light and energy. It is the arena in which all physical events unfold, and it carries rules far more intricate than anyone in the classical world imagined. As this new picture takes shape, the old assumptions fall away. The universe no longer offers a single universal time. Instead, every observer carries a personal measure of duration, shaped by how they move through spacetime. The old notion of absolute simultaneity dissolves, replaced by a deeper truth that events depend on the path taken by the observer. These discoveries were not philosophical reinterpretations. They were forced upon the scientific world by experiment, by observation, and by logic. Einstein embraced these consequences and built a structure that preserved every reliable prediction of the classical world while explaining every contradiction it failed to address. But this new understanding did more than rewrite the nature of time. It revealed a path toward understanding gravity itself in a way no one had previously considered. If motion could reshape time, and if time could influence motion, then perhaps gravity was not a force at all. Perhaps it was the result of space-time guiding objects along paths carved by the presence of mass. The seeds of that idea lie here, within the heart of special relativity, waiting to grow into the revolution that would soon redefine the universe. Time now begins to feel less like a constant flow and more like a quiet companion that adjusts itself to the journey you take. As you step deeper into this new landscape, you can sense how profoundly the discoveries of special relativity reshape the structure of reality. The classical world imagined time as a single river, moving at the same pace for all beings and all objects. But the evidence gathered across decades insists that time behaves more like a set of branching streams, each one shaped by the motion of the observer who travels through it. This idea may feel strange at first, yet it is grounded in experiments repeated countless times with unwavering results. The heart of this transformation lies in the constancy of the speed of light, a rule that nature enforces with remarkable precision. No matter how quickly you move toward or away from a beam of light, the speed you measure remains the same. This is not something your intuition prepares you for. In everyday life, speeds add and subtract with ease. If you run toward a throwing ball, it reaches you faster. If you run away, it reaches you slower. But light refuses to obey this familiar pattern. It moves as if space and time themselves cooperate to ensure that its speed never wavers. This cooperation between space and time reveals itself most clearly when you consider what must change as you approach the speed of light. Imagine you are traveling in a spacecraft that accelerates faster and faster, driving you toward that universal limit. As your speed increases, you might expect your experience of time to remain unchanged. Yet it does not. The faster you move, the slower your clock ticks compared to a clock at rest. This slowing does not distort your own experience. You do not feel your time stretching, but for those watching from a stationary frame, your seconds pass more slowly. Their seconds move swiftly, while yours drift gently, like leaves floating on a calmer stream. This effect is not theoretical. It has been measured in aircraft, satellites, and high-energy particle experiments. Moons formed in the atmosphere live far longer than they should because they move near the speed of light. Atomic clocks placed in fast-moving jets return to Earth ticking differently from the clocks that remained stationary. These observations are not approximations. They are precise confirmations that time dilation is woven into the structure of nature. And if time can stretch, then the distances that fast-moving objects experience must adjust as well. Length contraction emerges naturally from the need to preserve the speed of light. An object moving rapidly through space measures distances differently from a stationary observer, not because of illusion, but because motion changes the geometry of space-time. At first, these ideas might appear separate, like scattered pieces of a puzzle. But the moment you recognize that time and space cannot remain independent if the speed of light is universal, everything begins to align. Time dilation and length contraction are not isolated effects. They are the natural consequences of merging space and time into a single entity. Space-time provides a unified framework where events unfold along paths called world lines, each one shaped by the motion of the observer. This four-dimensional structure ensures that the laws of physics hold true for everyone, even when their motions differ wildly. Within this new framework, simultaneity becomes relative. Two events that appear to happen at the same moment for one observer may not be simultaneous for another who moves differently. This does not create contradiction. It reflects the reality that different observers carve distinct paths through space-time, experiencing its rhythm in their own way. The universality of time dissolves, replaced by a deeper order that preserves the fundamental laws, even as it allows each observer to carry a personal measure of duration. Once you accept this, the classical picture of space and time starts to feel limited. It offered clarity, but only within a narrow range. It described the motions of planets and falling objects, but it could not explain why time bends around velocity or why light refuses to change its pace. Special relativity solves these mysteries without breaking any of the successful predictions of the past. It honors the classical world, where its approximations remain valid, and extends the structure of physics into realms where the old assumptions fail. Einstein saw something more within this framework. He realized that if motion could reshape time, and if time were linked inseparably to space, then the path an object follows must depend on the geometry of space-time itself. This is where the seed of a far greater idea begins to take root. If space-time can adjust its measure of time and distance based on motion alone, then it might also adjust its shape in the presence of mass. And if it can do that, then gravity need not be a force reaching across space. It could simply be the natural motion of objects following the curves carved by matter. The beauty of this realization is that it emerges not from speculation, but from evidence. Every contradiction that troubled the classical world becomes a stepping stone toward a deeper understanding. Every measurement that resisted explanation becomes a guidepost pointing toward a universe more intricate than anyone imagined. Special relativity opens the door to this new universe, revealing that time and space are flexible, consistent, and deeply connected. And now, with this foundation in place, you stand on the threshold of a revolution that will reveal gravity itself in an entirely new light. Time now unfolds around you like a landscape that changes shape as you move through it. With every step into this new understanding, the universe feels less like a rigid stage and more like a living structure, responsive and interconnected. The discoveries you have followed so far reveal a truth that once seemed unimaginable. Time is not universal. Space is not fixed. The two blend together into a single fabric that bends gracefully to preserve the laws that govern light. As strange as this may feel, it is the only picture that aligns with every experiment, every measurement, and every observation gathered across the modern scientific world. Imagine two observers drifting through space. One remains still, while the other travels swiftly. Their experiences of time unfold differently. The moving observer feels no change within, yet the stationary one sees that the traveler's clock ticks more slowly. This difference does not arise from mechanical flaw or illusion. It emerges because the universe reshapes the flow of time to ensure its laws remain consistent for all frames of motion. Special relativity reveals this reshaping with clarity, showing that time adjusts itself with remarkable precision depending on velocity. Now imagine these observers comparing distances. The one who moves quickly through space finds that landmarks appear closer along the direction of motion, as if space shrinks to accommodate the high-speed journey. This contraction is not a visual trick. It is a physical change in the geometry experienced by the moving frame. It arises naturally from the structure of space-time and ensures that the speed of light remains constant for all observers. These effects may feel counterintuitive, yet they have been measured so many times that they stand as unshakable truths. Particle accelerators rely on them. Satellite networks account for them. The modern world depends on the accuracy of these principles every day. As these consequences unfold, a deeper unity begins to reveal itself. The old idea that space and time are separate fades into the background, replaced by a seamless, four-dimensional continuum. This continuum determines how events connect, how objects move, and how energy flows. The geometry of space-time becomes the foundation on which all physical interactions must be built. In this geometry, the path an object takes is not chosen by force alone. It is shaped by the texture of the space-time it travels through. Straight lines in this geometry become world lines, pathways that represent the natural motion of objects across time and space. This insight leads to one of the most profound realizations in the history of science. If motion can gently influence the way time passes and the way space measures distances, then perhaps mass and energy can influence the shape of space-time itself. The classical world imagined gravity as a force pulling objects toward each other. But in the context of space-time, this pull begins to look more like a curvature, a bending of the fabric through which objects naturally move. What we experience as falling might not be a tug from an invisible force, but the simple consequence of following the natural curve of space-time shaped by nearby mass. Einstein sensed this possibility long before he proved it. He understood that if space-time adjusts to preserve the speed of light, then it must also respond to the presence of matter. This idea did not emerge from speculation. It emerged from necessity. The contradictions of the classical world could not be resolved without recognizing that time and space must be dynamic. To preserve consistency, space-time must be allowed to curve, stretch, and shift. And if space-time can curve, then gravity becomes a question of geometry rather than force. Within this realization lies the seed of a revolution that would redefine the nature of the universe. Special relativity shows that the universe preserves its rules by reshaping the very fabric through which motion occurs. It lays the foundation for a new understanding where gravity and geometry become one. It reveals a universe that is coherent, elegant, and profoundly interconnected. Every strange consequence arises from logic, not invention. Every shift in time or length is measured, not imagined. Special relativity is the doorway through which the old world begins to dissolve and the new one begins to emerge. Einstein would soon step through that doorway, carrying with him the insight that would change everything. If space-time can respond to motion, it can also respond to mass. And if it can respond to mass, then gravity itself may be nothing more than the shape of space-time, guiding every object along the path it was always meant to follow. Before you step into this chapter, let your mind settle for a moment on the image of a traveler drifting freely inside a sealed room. unaware of any walls, unaware of any floor or ceiling. If that traveler releases an object and it floats beside them, does it mean gravity has vanished? Or does it mean they have entered a state where gravity reveals its true nature, silent and invisible, not as a force, but as the natural motion through a curved fabric they cannot see? This simple question, born from a thought experiment, would open the path toward one of the most profound ideas ever uncovered about the structure of the universe. Einstein understood that to move beyond the limits of the classical world, he needed to rethink gravity from its foundation. Special relativity had already shown that space and time cannot remain rigid. They must bend gently to preserve the speed of light, shaping themselves around the motion of every observer. But gravity demanded something even deeper. If it were to fit into this new framework, it could not be an instantaneous pull acting across empty space. It needed to emerge naturally from the geometry of space-time itself. The old picture imagined gravity as a force reaching outward. Einstein sought a picture where nothing reached and nothing pulled, where objects simply followed the shape of the environment that mass created around them. The key to this vision came from the idea of equivalence, the insight that free fall and weightlessness are indistinguishable. If you stand on the surface of the earth, you feel your weight. But if the ground were removed and you were allowed to fall freely, the sensation would vanish. You would feel nothing at all, as if gravity had disappeared. Yet you would still be carried downward, following a path etched into space-time by the Earth's mass. This strange pairing, weight without free fall and free fall without weight, reveals that weight is not the sign of gravity. It is the sign of resisting motion. True gravitational motion is weightless motion. It is the natural drift through curved space-time. Einstein realized that this simple observation held the key to unifying gravity with special relativity. If free fall is indistinguishable from weightlessness, then gravity acts not by pulling objects downward, but by shaping the paths they follow. Mass tells space-time how to curve, and curved space-time tells objects how to move. This idea may feel abstract, but it aligns perfectly with what we observe. A planet does not orbit the sun because of an invisible hand tugging at it. It orbits because space-time near the sun curves gently inward, guiding the planet along a natural line of motion. The planet is not being forced into this path. It is simply following the geometry that mass has sculpted. This explanation resolves contradictions the classical world could not escape. Gravity no longer needs to act instantaneously. Changes in the curvature of space-time travel at the speed of light, preserving the fundamental limit set by electromagnetism. The drift of Mercury becomes understandable because the space-time near the sun is more curved than classical equations predicted. Light bends as it passes near massive bodies, not because it is pulled, but because it follows the shortest path through a curved environment. Every puzzle that once resisted explanation becomes a natural consequence of letting gravity arise from geometry rather than force. Yet Einstein needed more than insight. He needed equations capable of describing how mass shapes space-time and how space-time guides motion. Creating these equations was not a quick achievement. It was a decade-long struggle filled with wrong turns, glimpses of truth, and moments of quiet revelation. The mathematics required to describe curved geometry had existed since the 19th century, but it had never been used to describe the physical world. Einstein took these mathematical tools and used them to craft a structure where space-time could stretch, twist, and bend. In this structure, mass determines the curvature, and curvature determines the motion of everything within it. When the final equations emerged, they carried a power that astonished even Einstein. They reduced to Newton's law in gentle environments, preserving every success of the classical world. But in regions of strong gravity, or where speeds approach the speed of light, they revealed a richer universe hidden beneath the surface. These equations predicted how Mercury moves, how light curves, how time slows in gravitational fields, and how the universe itself expands. They created a framework that matched every observation made since and predicted phenomena that would only be confirmed decades later. As you follow these ideas, the universe begins to feel different. Space is no longer an empty backdrop. Time is no longer a steady rhythm. Gravity is no longer a force pulling downward. Everything is geometry. Everything is motion along curves carved into a fabric that responds to mass and energy. The simplicity of this picture does not diminish its depth. It reveals a universe that is coherent, elegant, and far more interconnected than anyone imagined before Einstein. And now that this new vision has taken shape, the next step is inevitable. A theory, no matter how beautiful, must face the sunlight of experiment. The universe will either bend to match Einstein's predictions or refuse them. What happens next will determine whether this revolution stands or falls. Einstein's vision now begins to unfold like a vast landscape, one where every hill and valley is carved not from soil, but from the shape of space-time itself. As you move deeper into this world, you can feel the shift from force to geometry taking hold. It changes the way you imagine every motion, every orbit, every fall. The universe no longer behaves like a system of pulls and pushes. Instead, it behaves like a grand terrain, and every object moves along the curves of that terrain exactly as water flows through a valley. Nothing needs to reach across distance. Nothing needs to tug. The shape of space-time does all the guiding. To appreciate the power of this idea, imagine standing in a quiet field at night. You look upward at the stars. Each point of light seems fixed in its place, yet every star is moving along a path determined by the geometry shaped by all the mass surrounding it. Even your own body, standing still on the ground, is following a path through space-time. The earth beneath you is curving that path, pushing upward against your natural motion. The sensation of weight you feel is not gravity acting on you. It is the resistance of the ground preventing you from drifting freely along the path space-time has laid for you. This single shift in interpretation transforms the familiar into something deeper, something that reveals how the universe truly works. Einstein expressed this in terms that were both poetic and precise. Mass tells space-time how to curve, and curved space-time tells mass how to move. This simple line captures the essence of a theory that took a decade to sculpt. The mathematics that describe this curvature are intricate, yet the idea behind them is surprisingly intuitive. Just as a heavy ball placed on a stretched fabric creates a dip that guides smaller balls toward it, mass placed in space-time creates curvature that guides objects along natural paths. The difference is that space-time is not a fabric made of threads. It is a geometric structure that exists everywhere, shaping motion even when no material surface is present. Einstein knew his theory needed more than elegance. It needed to make predictions that could be tested. One of the earliest tests came from the orbit of Mercury, the same anomaly that had troubled astronomers for decades. When Einstein applied his equations to the Sun and its gravitational influence, they predicted exactly the additional drift that Mercury displayed. This was not a coincidence. It was a sign that the geometry of space-time near the Sun was more complex than Newtonian ideas could capture. For the first time, the drift was no longer a mystery. It was the natural result of Mercury following a curved space-time shaped by the intense gravity near the Sun. Another prediction came from the effect of gravity on light. Classical physics could not fully explain why light bends when it passes near a massive object. But in the geometry of general relativity, light follows the shortest path available, and when space-time curves, the shortest path curves with it. This prediction set the stage for an experiment that would take place during a solar eclipse, when starlight would pass close to the Sun and reveal whether Einstein's equations matched reality. But that moment comes later in our journey. For now, it stands as a signpost pointing toward the strength of a theory still waiting to be tested. Einstein also realized that time must slow in the presence of gravity. If space-time curves, then the flow of time curves with it. Clocks run more slowly near massive bodies, not because of mechanical effects, but because the very structure of time stretches in a gravitational field. This slowing has been measured with extraordinary precision using atomic clocks placed at different altitudes. Time itself passes differently depending on how deep you stand within a gravitational well. What once seemed unimaginable becomes a measured fact of nature. The elegance of general relativity lies in how naturally it resolves the contradictions that troubled the classical world. Gravity is no longer instantaneous. Changes in curvature move at the speed of light, preserving the universal limit. Time is no longer absolute. It shifts depending on motion and gravity, aligning with the evidence gathered across decades. Space is no longer rigid. It responds to mass and energy, guiding motion without the need for an external force. Each piece of the puzzle now fits together, creating a picture that is coherent and complete within its domain. Einstein knew the theory must reduce to Newton's laws when gravitational fields are gentle and speeds are ordinary, and it does. The equations of general relativity fold into the familiar classical form when space-time curvature is mild. This ensures that the new theory does not replace the old one, but extends it, carrying its successes into regions the classical world could never reach. The universe now becomes a place where the familiar and the extraordinary coexist, each governed by the same underlying principles, each shaped by the geometry of space-time. As this chapter unfolds, you begin to sense that the world Einstein revealed is not just a theory, it is the foundation upon which the modern understanding of the cosmos rests. But a theory this bold must face experiments capable of confirming or challenging its predictions. The story now turns toward those tests, where nature itself decides whether Einstein's vision reflects reality or simply imagination. Einstein's new universe now stretches around you with a clarity that feels both unfamiliar and inevitable, as if the cosmos had been waiting patiently for someone to notice the deeper structure beneath its surface. The more you let this vision settle, the more the old picture of gravity begins to dissolve. The idea of a pull acting across emptiness fades into the background, replaced by the realization that motion itself is shaped by the geometry of space-time. This is not merely a reinterpretation. It is a transformation in the way reality presents itself. To sense this transformation, imagine releasing an object in deep space, far from any star or planet. With no forces acting upon it, the object drifts along a straight line at a steady speed. This is the natural motion described by special relativity. But place the same object near a massive body and its path curves, not because anything reaches out to tug at it, but because the space-time around the mass is curved. The object still follows the straightest possible line in that curved geometry. The path appears bent only because the space is bent. This is the heart of general relativity. Gravity becomes a matter of geometry, not force. Einstein built this idea by following a chain of reasoning so simple that it reveals its power only after you understand its consequences. He began by trusting the equivalence principle, the idea that free fall is indistinguishable from weightlessness. This principle suggests that gravity does not act like other forces. In free fall, gravity seems to vanish entirely. If gravity were a true force in the classical sense, you would feel it no matter what. But you do not. You feel nothing at all while falling freely. You feel weight only when the ground pushes against you. This insight becomes a doorway into understanding that gravity does not act directly on the body. It shapes the space-time through which the body moves. From this doorway emerges a vision where every object, from a falling apple to a drifting galaxy, traces the natural curves of space-time. These curves are called geodesics, the paths that minimize or maximize the measure of time experienced by the moving object. A planet orbiting a star is not being forced into a loop. It is following the geodesic carved by the star's mass. Light passing near a massive body does not bend because a force pushes it sideways. It bends because the straightest path through a curved environment is itself curved. Even beams of light, which have no mass, respond to the shape of space-time. because their paths are woven into its geometry. With each of these consequences, the universe becomes more elegant. Every motion becomes a dialogue between mass and geometry. Every orbit becomes a story written in the curvature of space-time. Every measurement of time becomes a reflection of the depth of the gravitational field. Clocks run slower near massive bodies because time itself has stretched. This stretching has been confirmed through experiments with astonishing precision. Atomic clocks lifted gently from the ground tick faster than the ones left below. Time is not a universal rhythm. It is shaped by the curvature that mass creates. Einstein's equations capture all of this with profound simplicity. They describe how mass and energy determine the curvature of space-time, and how that curvature determines the motion of everything within it. These equations are demanding to solve, but their meaning is clear. They create a bridge between geometry and physics, turning what once seemed like abstract mathematics into the language of nature itself. They reveal black holes, gravitational waves, and the expansion of the universe, phenomena that the classical world could neither predict nor imagine. Yet the power of general relativity does not lie in its beauty alone. It lies in its ability to match the world we observe. Every prediction made by the theory has been tested through experiments and astronomical observations. Each test has reinforced the truth of Einstein's vision. From the drift of Mercury to the bending of starlight, from the slowing of time in gravitational fields to the ripples in space-time detected by modern observatories, the universe continues to affirm that gravity is geometry. As you reach the end of this chapter, the transformation is complete. The classical world, with its rigid space and absolute time, has given way to a universe more fluid and more intricate. The new picture does not discard the old. It contains it, extends it, and deepens it. It shows that the familiar motions you see every day are the surface of a deeper structure, one where the universe speaks through curvature rather than force. And now the journey turns toward the moment when these ideas left the realm of theory and entered the realm of observation. When the sunlight of a distant morning revealed that the geometry Einstein had drawn was not imagination but reality. Before you step deeper into this chapter, imagine a world standing at the edge of uncertainty. A theory as bold as general relativity has taken shape, claiming that gravity is not a force but a curvature of space-time. Yet at the moment of its birth, it exists only as mathematics and imagination. What would it take to convince the world that space truly bends and time truly slows? What kind of evidence could reveal a universe shaped not by invisible pulls, but by geometry itself? The answers would come not from belief, but from sunlight, starlight, and measurements made with patience and precision. As the 20th century opened, Einstein's theory faced its first great test. It had already offered explanations for puzzles that the classical world could not solve. It predicted the correct drift of Mercury, matching a value that had evaded every attempt rooted in Newton's ideas. But this success, though remarkable, was not enough. The scientific world demanded something more direct, something that could not be dismissed as coincidence or clever adjustment. It needed a prediction bold enough to risk failure, yet grounded enough to invite a decisive experiment. That prediction came from the idea that light follows the curvature of space-time. According to general relativity, a beam of starlight passing near the sun should bend by a measurable amount. The classical world had guessed a smaller bending, but Einstein predicted roughly twice that value. The difference was not subtle. It was the kind of disparity that could reveal whether the universe obeyed the old rules or the new ones. Nature would provide the answer, but only under the right conditions. The brightness of the sun hides the stars near its edge, making them impossible to observe. The only way to measure the bending was to wait for a total solar eclipse, a rare alignment that briefly dims the sun enough for stars to appear around it. In 1919, as the world emerged from war, an expedition led by Arthur Eddington set out to test this prediction. They traveled to remote islands where the eclipse would be visible. carrying delicate instruments capable of capturing the positions of stars during the brief darkness. The day arrived, the sky dimmed, and the stars around the sun's shadow revealed themselves. Measurements were made with painstaking care, comparing the positions of these stars during the eclipse to their normal positions in the night sky. When the results were analyzed, they confirmed Einstein's prediction. The light had bent by the amount demanded by general relativity. Space had curved in the presence of mass. News of this result spread quickly, and Einstein became a figure recognized far beyond the world of physics. But the evidence from 1919 was only the beginning. Over the decades that followed, general relativity faced test after test, each one probing a different corner of nature, each one offering nature another opportunity to disagree. Yet time and again, the universe aligned with Einstein's equations. One of the most striking confirmations came from the behavior of light in gravitational fields. If spacetime curves, then light traveling upward from a source deep within a gravitational well should lose energy. This loss does not slow the light, since its speed remains constant. Instead, it stretches the wavelength, shifting the light toward the red end of the spectrum. This effect, known as gravitational redshift, was predicted by general relativity and later confirmed through the Pound-Rebka experiment, which measured tiny shifts in gamma rays emitted from different heights within a tower. The results matched the prediction with extraordinary precision. Another confirmation arrived from the heavens. Binary star systems, where two dense objects orbit one another, behave like cosmic laboratories for testing gravity under extreme conditions. In one such system, a pair of neutron stars orbiting rapidly produced a slow loss of orbital energy over time. This loss matched exactly what general relativity predicted, showing that the system was emitting gravitational energy into space, even though no instrument on Earth could yet detect such waves directly. The agreement was so precise that it earned a Nobel Prize. The evidence continued to grow as technology advanced. Clocks flown around the world ticked differently from those left on the ground, confirming both the effects of motion and the effects of gravity on time. Satellite networks required adjustments predicted by general relativity to function accurately. If engineers ignored these effects, systems would drift into chaos, with positioning data failing within hours. The universe does not merely hint at the curvature of spacetime, it insists upon it. General relativity even reshaped the way astronomers observe distant galaxies. Massive clusters of matter can bend light from galaxies behind them, creating arcs, rings, and magnified distortions known as gravitational lenses. These patterns allow scientists to map the distribution of mass, including mass that cannot be seen directly. The sky is filled with these cosmic signatures, each one a visual echo of curved spacetime. Newtonian physics cannot account for them. Einstein's equations describe them effortlessly. With each passing decade, new experiments reinforce the same message. Gravity Probe B confirmed the subtle twisting of spacetime caused by the Earth's rotation. Pulsar timing arrays revealed gravitational disturbances rippling across the galaxy. Every test, whether delicate or monumental, pointed toward the truth that Einstein had uncovered. And as you stand here at the end of this part of the story, you can feel the weight of that truth settling into place. The universe has spoken through eclipses, clocks, starlight, and the motions of distant stars. It has declared that spacetime is not rigid. It bends and curves, and gravity is the shape of that curvature. But even these confirmations tell only part of the story. For the universe contains environments where spacetime bends far more dramatically, places where Einstein's equations reveal phenomena stranger and more extreme than anything imagined before him. Einstein's theory now stands in the light of repeated confirmation, yet the story of its validation is far from finished. The early eclipse expedition offered a dramatic beginning, but the true strength of a scientific idea lies in its ability to endure across decades, across technologies, and across environments far beyond the imagination of its creator. As you move deeper into this unfolding journey, you can feel the universe revealing more of its structure, guiding you toward regions where time slows, light bends, and the familiar logic of the classical world quietly gives way to the deeper language of space-time. Imagine standing before a tall tower with a source of high-energy light at its base. According to general relativity, light climbing upward through a gravitational field must lose a small amount of energy. It does not slow down, for the speed of light remains constant in all frames. Instead, its wavelength stretches, shifting the color gently toward the red end of the spectrum. This prediction seemed nearly impossible to test when Einstein first proposed it, for the shift is subtle, almost whisper-soft. Yet decades later, the Pound-Rebka experiment measured precisely this effect by sending light upward and downward inside a tower, demonstrating that the universe behaves exactly as Einstein's equations dictate. Gravity alters the very rhythm of light. These shifts are not limited to laboratory towers. They influence every signal that climbs upward from the Earth's surface. Clocks placed at higher altitudes tick faster than clocks near sea level. This difference is tiny, yet measurable with atomic precision. It arises because time flows more quickly in regions where space-time is less curved. When engineers designed global positioning systems, they discovered that satellites orbiting high above the Earth experience time at a slightly faster rate than clocks on the ground. If these differences were not corrected, the positioning system would drift into error within hours. The fact that this technology functions at all is a daily confirmation of general relativity. But the confidence in Einstein's theory does not rest only on terrestrial experiments. The universe offers environments far more extreme than anything on Earth, and these environments act as natural laboratories for testing gravity under intense conditions. Consider a binary system where two neutron stars orbit one another with astonishing speed. Each star is the remnant of a massive sun, crushed into a sphere barely larger than a city, containing mass so dense that a teaspoon would outweigh mountains. Their rapid orbits produce enormous gravitational fields, and Einstein predicted that such systems should emit gravitational energy outward into space. This energy loss would cause the stars to spiral inward at a precise, measurable rate. When astronomers observed such a system, they found exactly that behavior. The orbit decayed in perfect agreement with general relativity. The timing matched to extraordinary precision, confirming that gravitational waves were real long before they could be detected directly. This discovery earned a Nobel Prize, not because it was dramatic, but because it demonstrated the predictive power of a theory that had already withstood decades of scrutiny. The sky itself provides further evidence through gravitational lensing, an effect that turns entire regions of the cosmos into natural telescopes. When light from distant galaxies passes near massive clusters, the curved spacetime distorts its path. The galaxies appear stretched, magnified, or multiplied, forming arcs and rings that reveal the invisible structure of mass in the universe. These cosmic shapes cannot be explained by classical physics. They follow the exact patterns predicted by Einstein's equations, allowing scientists to map not only visible matter, but also unseen mass that leaves no light of its own. Each of these confirmations deepens the sense that the universe is not merely agreeing with Einstein. It is speaking through phenomena that exist on scales ranging from laboratory floors to the farthest reaches of space. Even the rotation of the Earth leaves a subtle imprint on space-time, twisting it slightly in a manner predicted by general relativity. Gravity Probe B, an experiment involving ultra-precise gyroscopes orbiting the Earth, measured this tiny effect. The gyroscopes drifted in the exact way the curved and twisted space-time demanded. Once again, experiment and theory aligned. These results form a pattern that is impossible to ignore. The universe bends light. It shifts time. It curves the paths of objects in ways that reveal the geometry of space-time. Einstein's ideas did not merely solve old puzzles. They offered a framework capable of describing phenomena that had never been observed before. And each new observation, whether on Earth or across the cosmos, reinforced that the geometry he described is woven into reality. Yet even with all this evidence, the story of testing general relativity continues. Nature reserves its most dramatic confirmations for environments where gravity grows immensely strong, where mass compresses into unimaginable densities, and where space-time stretches and twists with ferocity. These environments were once theoretical curiosities, but they would soon reveal themselves in the form of black holes, neutron-star collisions, and gravitational waves rippling across the universe. The universe now stands before you like a vast experiment, unfolding evidence across every scale, from the quiet ticking of atomic clocks to the roaring gravity of collapsing stars. Each confirmation of general relativity feels like another piece of a mosaic clicking into place, revealing a picture that grows sharper the more you look. Yet the story of proving Einstein's theory does not end with gentle shifts in time, nor with the bending of light during eclipses, nor even with the steady energy loss in distant binary systems. The deepest tests lie in regions where gravity becomes overwhelming, where space-time bends so sharply that its structure approaches the limits of what can be measured. Here, nature reveals its most dramatic agreement with Einstein. Imagine a telescope pointed toward a massive galaxy cluster millions of light years away. The galaxies behind the cluster appear distorted, stretched into arcs and rings that curve gracefully across the sky. These features, known as Einstein rings, are produced when space-time bends so strongly that it magnifies and warps the light of more distant objects. Astronomers use these distortions to map not only visible matter, but also the unseen mass hidden throughout the universe. General relativity predicts the exact shapes these distortions should take, and observations match those predictions with remarkable precision. Every arc of bent starlight becomes a signature written by curved space-time. But lensing is only one piece of the story. The next comes from the timing of pulsars, spinning remnants of collapsed stars that beam out pulses of radio waves with clock-like regularity. When such a pulsar orbits a companion, the timing of its pulses shifts in ways that reveal the curvature of space-time around it. In some systems, the effects are so extreme that they allow scientists to test general relativity with unparalleled accuracy. The pulses slow and speed up as the pulsar moves through regions of stronger or weaker gravity. The orbit precesses, turning gradually in a way that mirrors the behavior of Mercury, but with far greater intensity. Each of these effects matches Einstein's predictions down to tiny fractions of a second. These confirmations deepen further when scientists observe systems where one member is a neutron star and the other is a second neutron star, or even a black hole. The gravitational fields in such systems are fierce, yet the behavior of the orbit still follows the curves dictated by general relativity. The dance of these objects becomes a silent demonstration of space-time geometry at work, proving that the theory holds even in environments beyond anything Newton could have imagined. Even the surface of the Earth offers its own laboratory for extreme precision. Gravity Probe B measured how the rotating Earth drags space-time around with it, an effect known as frame dragging. This subtle twist, almost unimaginably small, required gyroscopes so stable that they could detect the smallest drift in their orientation over the course of many months. When the results came in, the drift matched what general relativity had predicted. The Earth, moving through space-time, had twisted the fabric around it in exactly the way the equations described. As the decades progressed, experiments began to reach for confirmations that had long been dreamed of, but never achieved. The idea that massive objects accelerating through curved spacetime should produce ripples in that spacetime had been one of Einstein's earliest predictions. These ripples, known as gravitational waves, spread outward from their source at the speed of light, carrying information about violent cosmic events. For many years, they remained unobserved, passing through Earth without leaving a trace detectable by any instrument available. Yet their influence was confirmed indirectly in the shrinking orbit of neutron star pairs, and scientists were certain they existed. Then came the development of enormous detectors capable of sensing distortions in space-time, smaller than a fraction of the width of an atomic particle. These detectors waited patiently for signals from the universe. And when the first gravitational waves finally swept through Earth, they revealed the collision of two black holes more than 1 billion light-years away. The signal matched Einstein's predictions in every detail, from the rising frequency to the sudden silence that followed the merger. The universe had spoken through space-time itself, and its voice echoed the geometry Einstein described. With each new detection, gravitational waves reveal more of the cosmos. They show black holes merging, neutron stars spiraling together, and matter crushed into densities that challenge the limits of physical theory. They confirm that gravity is not a pull, but a curve, not a force, but a consequence of space-time responding to mass and motion. No classical theory can account for these signals. Only general relativity carries the language capable of describing them. As you step back from these confirmations, the scale of the evidence becomes overwhelming. Every experiment, every observation, and every cosmic event aligns with Einstein's prediction that gravity is geometry. From eclipses to pulsars, from atomic clocks to merging black holes, the universe continues to affirm his vision. There is no single test that stands alone. Instead, there is a symphony of experiments, each playing a part in revealing the curvature of space-time. And yet, even as general relativity triumphs again and again, nature hints that its story is not complete. There are places where the theory reaches its limits, where curvature becomes infinite, and where the laws that govern space-time begin to break down. These places mark the edge of Einstein's universe, and they lead toward a deeper mystery waiting in the chapters ahead. Before you step into this chapter, imagine standing at the edge of a place where the universe stretches its laws to their limits, where gravity becomes so intense that it no longer behaves like gravity at all, and where time itself moves with a rhythm so slow that an outside observer might mistake stillness for eternity. What happens to the familiar rules when mass collapses so tightly that space-time folds inward upon itself? What lies beyond the boundary where even light cannot escape? And what does a place like this reveal about the true nature of gravity? To follow this path, you must return to the first exact solution ever discovered for Einstein's equations, a solution found not by Einstein himself, but by a physicist named Carl Schwarzschild. While serving on the front lines during a war, Schwarzschild solved the equations for a perfectly spherical mass. His solution described the curvature of space-time around such a mass with astonishing clarity. What he discovered in the mathematics was a region where the curvature became so steep that nothing, not even light, could climb out. This was not speculation. It was a strict consequence of the geometry implied by general relativity. At first, even Einstein doubted that such objects could exist in nature. The idea seemed too extreme, too distant from anything observed. But as the decades passed, evidence began to gather from the sky itself. Stars were seen dancing around invisible companions that exerted immense gravitational pull. Light from distant regions was shifted and distorted in ways that suggested enormous mass compressed into impossibly small volumes. Eventually, the combined weight of these observations made the existence of black holes not only plausible, but unavoidable. To picture a black hole, do not imagine a hole or a void. Imagine instead a region of space-time so curved that every path leads inward. Once an object crosses the boundary known as the event horizon, every future direction points deeper toward the center. No force, no engine, no burst of light can reverse that path. But outside this horizon, the universe remains accessible and predictable. Stars orbit as they always have. Light bends along curved paths, and time flows at different rates depending on how close one stands to the intense gravity. The evidence for stellar mass black holes comes from systems where a visible star orbits an unseen partner. By tracking the motion of the visible star, scientists can measure the mass of the hidden companion. In many cases, the mass is too great to be a white dwarf or a neutron star. The only remaining explanation is a black hole. Observatories around the world have found these systems scattered throughout the galaxy, each one a quiet confirmation that Einstein's geometry can produce objects far more extreme than anything the classical world imagined. Yet these stellar black holes are only the beginning. At the centers of galaxies, including the galaxy you inhabit, lie objects millions of times more massive than the Sun, compressed into regions smaller than the orbit of Mercury. Their influence can be measured by watching the stars that swirl around them. Near the center of the Milky Way, a star known to astronomers orbits a dark object with extraordinary speed, completing its path in a little more than a human decade. By measuring this motion, scientists have determined the mass of the hidden object to be millions of times that of the Sun. There is no known form of matter capable of containing such mass within so small a region. Only a supermassive black hole fits the evidence. The most striking confirmation came when the Event Horizon Telescope combined observations from telescopes across the Earth to create a planet-sized lens. This collaboration produced the first image of the shadow cast by a black hole against the glowing material around it. The image revealed a dark center encircled by a ring of light shaped by intense curvature. It matched the predictions of general relativity with remarkable accuracy. The brightness pattern, the size of the shadow, and the position of the luminous arcs all spoke the same message. Spacetime behaves near a black hole exactly as Einstein described. The physics near an event horizon grows stranger still. Time slows dramatically as one approaches the boundary. To an outside observer, a falling object appears to freeze just above the horizon, its clock ticking more slowly with every passing moment. But for the object itself, time flows normally, carrying it inward without any abrupt transition. This difference in perspective illustrates the profound effect that curvature has on the passage of time. It is not speculation. It is the natural consequence of general relativity and is supported by every experiment ever conducted on gravitational time dilation. Within the horizon, the curvature intensifies, eventually reaching a point where the equations of general relativity can no longer describe it. This point is known as a singularity, not because it has been observed, but because the mathematics predicts that space-time curvature becomes infinite. Physicists do not interpret this as a literal description of reality. Instead, it signals that Einstein's theory, however successful, must eventually give way to a deeper framework. Within the singular heart of a black hole lies the boundary where our current understanding ends. And yet, even without knowing what lies beyond that boundary, the universe continues to reveal the astonishing accuracy of the theory leading toward it. Black holes do not remain isolated. They collide, they merge, they twist space-time so violently that ripples spread outward across the cosmos. These ripples, known as gravitational waves, carry the imprint of their origin. They have been detected, measured, and confirmed. Each detection provides a direct probe of the most extreme gravitational environments known. In every case, the waves match the predictions of general relativity. As you stand here at the end of this part of the story, the universe feels more alive than ever. Black holes are not anomalies. They are natural consequences of curved space-time. They prove that general relativity extends far beyond gentle environments into regions of unimaginable intensity, and they open the door toward the next great realization, that space-time is not a silent backdrop, but a dynamic entity capable of vibrating, flexing, and sending its echoes across billions of years. The world of black holes now unfolds before you with a sense of awe that grows deeper the longer you look. These objects, once dismissed as mathematical curiosities, have become essential to understanding how gravity behaves when pushed to its extremes. They reveal that space-time is not merely curved, but capable of folding so sharply that the familiar structure of the universe seems to narrow into a single direction. Yet even in these extraordinary environments, every motion and every signal follows the same rules that guide planets, stars, and light itself. Gravity remains geometry, even when the geometry becomes almost impossibly steep. To sense the strange beauty of these regions, imagine drifting toward a black hole from a great distance. At first, nothing unusual reveals itself. The stars look the same. The space around you seems calm. The gravity you feel grows stronger, but not alarmingly so. Only as you draw nearer does the environment begin to shift. Light coming from behind you begins to curve around the edges of the black hole, creating a faint distortion in the sky. The paths of photons tighten, following the shape of the space-time well. The closer you come, the more dramatic this effect becomes, until the black hole appears surrounded by a glowing ring where light has been bent almost into a loop. Yet even this visual distortion is only a surface-level consequence of the curvature. Far more dramatic changes unfold in the behavior of time. From the perspective of an observer far away, your clock appears to slow as you descend deeper into the gravitational field. Seconds pass normally for you, but they stretch for the distant observer. Your voice, if sent outward, drifts into lower and lower frequencies, as if sliding into a cosmic whisper. This effect grows stronger until, near the event horizon, your flow of time seems to approach near stillness. The distant observer would never see you cross the boundary. You would appear frozen forever at the edge, slowly fading as your light stretches into longer wavelengths. But from your own perspective, nothing unusual happens at the horizon. You cross it without feeling a boundary, without sensing a barrier. The event horizon is not a physical surface. It is a geometric point of no return, a place where the curvature becomes so steep that all paths lead inward. Once past this point, every possible direction in space-time carries you closer to the center. The geometry has folded in such a way that outward motion is no longer an option, not because of a force pulling you inward, but because the structure of space-time itself no longer allows any other path. As you continue inward, the curvature intensifies. Space-time funnels all directions toward the central region, where the theory predicts a singularity, a place where the equations of general relativity can no longer describe the shape of space-time. This prediction does not represent an actual point of infinite density, for infinities in physics usually signal that the theory has reached beyond its domain. Instead, the presence of a singularity marks the frontier where Einstein's description of gravity must give way to a deeper understanding. It hints that a complete theory of gravity will require the tools of quantum physics, a subject that lies ahead in later chapters. Outside the event horizon, however, black holes influence the universe in ways that can be measured with extraordinary precision. Matter falling toward a black hole forms a swirling disk that heats to extreme temperatures, producing powerful radiation. These disks allow astronomers to identify black holes throughout the cosmos. Some of them power jets that shoot outward at nearly the speed of light, stretching across distances measured in hundreds of thousands of light years. These jets arise from magnetic forces and the twisting of space-time around rapidly spinning black holes. They provide yet another test of Einstein's equations, which describe how rotation drags space-time with it, creating a swirling geometry known as frame dragging. One of the most compelling confirmations of this effect comes from observing stars orbiting near the supermassive black hole at the center of the Milky Way. These stars move with extraordinary speed, tracing paths that reveal not only the mass of the black hole, but also subtle shifts in their orbits caused by space-time curvature. One star in particular follows a long, narrow path that brings it astonishingly close to the black hole before sweeping it back outward. Its motion aligns perfectly with the predictions of general relativity, showing that even at galactic scales, Einstein's equations describe the shape of space-time with remarkable accuracy. The Event Horizon Telescope image deepens this evidence further. The dark shadow at the center of the ring corresponds to the event horizon itself, while the glowing ring traces light bent around the black hole. The pattern is not random. It reveals the curvature, the rotation, and the structure of the space-time well. Every feature of the image mirrors the predictions of Einstein's theory. The universe, through this observation, confirms not only the existence of black holes, but the precise way space-time behaves around them. As scientists study these extreme environments, they also explore the edges, where Einstein himself knew his theory might break. Black holes create regions where density and curvature rise beyond anything that can be reached in a laboratory. They provide natural settings in which space-time becomes so sharply curved that new physics must eventually emerge. Quantum effects near the horizon create phenomena such as Hawking radiation, a prediction derived from combining quantum mechanics with curved space-time. This radiation has not yet been observed directly, but its theoretical foundation hints that the story of gravity may one day expand beyond general relativity. Yet even without this future understanding, black holes stand as one of the strongest confirmations of Einstein's vision. They reveal the behavior of space-time under conditions so extreme that no classical theory can describe them. They show that gravity is not a force that acts across a distance, but a shape that governs all motion. They remind you that the universe is not limited by human intuition. It is shaped by a geometry that grows more intricate and more astonishing the deeper you explore. The universe around a black hole now feels like a realm where the ordinary laws of nature reveal their hidden depths. As you journey farther into this extreme environment, you begin to sense how profoundly general relativity reshapes the meaning of motion, distance, and time. Every step closer to the event horizon carries you into regions where the familiar structure of space-time bends into forms that seem almost otherworldly. Yet every curve and every distortion remains a precise and predictable expression of Einstein's equations. Nothing here is invented. Nothing here is imagined beyond what the evidence and mathematics demand. Black holes stand as the purest demonstration of gravity as geometry. To understand the extremes more fully, imagine watching a pair of black holes spiral toward one another. Far from this cosmic dance, the motion appears serene, almost graceful. But closer in, the space-time around them twists and stretches with violent intensity. The two massive objects draw inward as they lose energy through ripples in space-time. These ripples, known as gravitational waves, move outward in all directions at the speed of light, carrying away the imprint of the orbiting pair. The closer the black holes drift, the faster they move, and the louder the waves become in the language of space-time. This crescendo grows until the two objects finally merge, forming a single, larger black hole. The vibrations of space-time fade, leaving behind a new geometry, smooth and transformed. This entire sequence was predicted by Einstein's theory long before anyone had the instruments to measure it. And when detectors finally heard these waves for the first time, the pattern matched the theoretical prediction with astonishing accuracy. The frequency, the amplitude, and the final calm following the merger all reflected the shape of the equations. The waves revealed not only the masses of the black holes, but also how fast they were spinning, how quickly they lost energy, and how space-time behaved in the aftermath. These observations stand as some of the most direct confirmations ever made of general relativity under conditions that push gravity to its limits. But black holes also reveal their presence through quieter signs. Gas spiraling toward a black hole forms an accretion disk that heats to extreme temperatures. The radiation from this disk varies in brightness as the gas moves through regions of intense curvature. These variations offer a way to measure the spin of the black hole and the depth of the gravitational well. Observations from space-based telescopes reveal that the inner edge of the disk sits closer or farther from the event horizon depending on the black hole's rotation. This relationship arises directly from the geometry of the space-time around the black hole. The faster it spins, the closer matter can orbit before plunging inward. These detailed measurements do not merely suggest that black holes exist, they show that space-time behaves near them exactly as general relativity predicts. The motions of the gas, the timing of the brightening, and the shape of the emission all follow from the curved geometry described by the theory. Even the shadows cast by the black holes in the images obtained by the Event Horizon Telescope reveal how photons loop around the event horizon before escaping toward Earth. The brightness pattern in those images reflects not only the mass, but also the spin, the orientation, and the structure of the space-time well. Everything matches the mathematics, and yet these confirmations reveal more than the power of general relativity. They show where the theory reaches its frontier. At the center of a black hole, the equations predict a region where curvature grows without bound. This does not mean nature contains infinities. It means that general relativity has reached an edge where it can no longer describe the physical world. The singularity is a sign that another layer of physics must exist, one that unites the quantum world with gravity. Black holes point toward this deeper structure, hinting that space-time has properties still hidden from us, properties that do not appear in the calm environments where gravity is gentle. This frontier becomes even more fascinating when you consider the behavior of information near a black hole. Though this topic reaches beyond the strictly classical picture, one thing remains certain from observations. Matter falling into a black hole influences its mass, its spin, and the shape of its event horizon. These changes can be measured from the outside. The geometry of the black hole carries the imprint of everything that has crossed the horizon, even if the internal details remain hidden. This influence reinforces the idea that black holes are not mere voids. They are active space-time structures capable of interacting with their surroundings in ways that align with general relativity. As you draw back from these extremes, a clearer picture emerges. Black holes are not exotic outliers. They are natural consequences of Einstein's geometry. They form when massive stars exhaust their fuel and collapse under their own gravity. They grow when matter falls inward. They merge, creating gravitational waves that travel across billions of years. They shape the centers of galaxies and influence the flow of matter across enormous regions of space. With every observation, the universe reveals that Einstein's description of gravity remains accurate even in the most violent environments known. Yet these environments also highlight the limits of the theory. They show that space-time can curve so steeply that the classical description reaches a boundary. Beyond that boundary lies the question of how gravity behaves when quantum effects dominate, a question that leads to a deeper challenge, finding a theory that unites the geometry of space-time with the principles governing the smallest scales of nature. The universe now stands at the threshold of this mystery, and your journey continues with it, moving toward the places where general relativity meets its limits and where the search for a deeper understanding begins. Before you step into this chapter, imagine the universe not as a silent expanse, but as a place filled with vibrations, gentle and fierce, rippling through space-time itself. These vibrations have been traveling across the cosmos for billions of years, passing through galaxies, drifting through nebulae, weaving through regions where stars are born and where stars collapse. They reach Earth so faintly that they stretch and compress distances by amounts smaller than the width of a single atomic particle. Yet within these subtle ripples lies a message, a record of events so violent that they reshape the galaxies around them. What would it mean to hear the universe through these waves rather than through light? What new truths might the cosmos reveal when observed through the rhythm of space-time itself? Gravitational waves were first predicted by Einstein in the early years of general relativity. When two masses accelerate, especially when they move in tight orbits, their motion disturbs the curvature of space-time. This disturbance spreads outward in all directions at the speed of light. The waves do not carry matter. They carry changes in geometry. They stretch space-time slightly in one direction while compressing it in another, passing silently through everything they encounter. In the early 20th century, this idea seemed nearly impossible to test. The distortions were expected to be so small that no instrument could detect them. Yet the universe contains events powerful enough to generate waves strong enough to reach across cosmic distances. Long before the technology existed to detect these waves directly, astronomers saw their influence in distant binary systems. The most famous example came from a pair of neutron stars orbiting so rapidly that their motion revealed a gradual loss of orbital energy. This loss matched the exact amount of energy that general relativity predicted should be carried away by gravitational waves. The orbit shrank steadily over time, drawing the stars closer in a dance that reflected the geometry of spacetime. The precision of the match left no doubt. Even without hearing the waves themselves, scientists could see the imprint of their passage. The challenge was to detect the waves directly, to measure the stretching and compressing of spacetime as a wave passed through the Earth. This required instruments capable of sensing changes smaller than anything ever measured. Engineers built enormous detectors that used laser beams to track these subtle distortions. Long arms extended in perpendicular directions, allowing scientists to measure how each arm stretched or shrank compared to the other. These detectors, placed miles apart, needed to remain still enough to sense disturbances far weaker than the vibrations caused by footsteps, distant trucks, or even the shifting of the ground itself. It took decades of development, but the instruments finally reached the sensitivity required. Then, one morning, a signal arrived. A ripple passed through Earth, stretching and compressing the detectors by an amount so incredibly small that it could only be measured with instruments designed to capture the faintest motion. The pattern of the signal matched the prediction of two black holes spiraling inward, colliding, and merging into a single new black hole. The frequency of the wave rose steadily as the black holes drew closer, then fell silent after the final merger. The universe had spoken through space-time, and the detectors had heard its voice. This first detection opened a new way of observing the cosmos. It confirmed not only the existence of gravitational waves, but also the ability of general relativity to describe events of extraordinary intensity. Since that moment, detectors have captured many more waves, revealing collisions of black holes, mergers of neutron stars, and even events where matter and gravity interact in complex ways. Each detection provides a new set of clues about the behavior of spacetime under extreme conditions. Each one strengthens the evidence that gravity is not a force, but a curvature of spacetime that changes and vibrates when massive objects move. The merger of neutron stars brought an especially powerful confirmation. Unlike black hole collisions, which release no light of their own, neutron star mergers produce both gravitational waves and electromagnetic radiation. When detectors heard the gravitational waves from such a merger, telescopes around the world turned to the same region of the sky. They saw a burst of light, followed by radiation across the spectrum. The timing and energy matched the predictions of general relativity and nuclear physics. It revealed that such collisions create heavy elements, seeding the universe with materials like gold and platinum. The waves provided the physical narrative, while the light provided the visual story. Together, they formed a complete picture of an event far beyond the reach of classical physics. As gravitational wave astronomy expands, it opens windows onto regions of the universe once hidden from view. Light can be blocked, absorbed, or scattered, but gravitational waves pass through dust, gas, and even the densest regions of space without being stopped. They offer a way to observe the universe as it truly behaves, without interference, without distortion. They reveal black holes merging far beyond the reach of traditional telescopes. They trace the motions of massive objects with clarity that no other method can match. They carry the geometry of the universe itself. Every detection reinforces the truth that Einstein described. Gravity is not a force. It is a curvature that can vibrate, stretch, and ripple. When these ripples reach Earth, they do not behave like sound or light. They behave like changes in the structure of space and time. They confirm that mass shapes geometry, and geometry determines motion. They show that general relativity remains accurate even in the most violent environments known. Yet even this triumph does not close the story. These waves reveal the universe through a new sense, but they also hint at deeper structures still hidden. They whisper of regions where space-time behaves in ways not yet understood, where the limits of the theory will once again be tested. The universe now feels alive with motion you cannot see, carrying vibrations that pass effortlessly through everything that exists. As you step deeper into this chapter, the idea of listening to gravity begins to feel as natural as watching light. Gravitational waves reveal a universe where space-time is not a silent backdrop, but a restless medium that stretches and contracts with every massive motion. These waves are faint, unimaginably faint, yet each one carries the signature of a cosmic event so powerful that its echoes reach across billions of years. To understand this world more fully, you must slow down and let the rhythm of space-time guide you. Imagine a pair of black holes circling one another. At first, their motion is slow and broad, the arcs wide and gentle. The waves they produce drift outward softly, spreading through the universe with rhythm so low that no instrument of the past could ever hope to hear it. But as the black holes spiral closer, their motion accelerates, their orbit tightens. The curvature around them deepens. The waves grow louder in the geometry of space-time, rising in frequency as the pair draws inward. The entire scene becomes a kind of cosmic heartbeat, a steady thudding woven into the structure of space-time. If you were standing far away, floating peacefully in the vacuum near some quiet star, you would not feel these waves directly. They would pass through you unnoticed, stretching and compressing your surroundings by an amount so small that your senses could never detect it. Yet if you carried instruments like those on Earth, instruments capable of measuring changes at scales beyond human perception, you would see space-time ripple gently around you. The wave would pass silently, leaving behind a slight shift in distance that lasts only as long as the wave itself. These passing waves do not carry matter, heat, or particles. They carry information about how space-time was shaped at the moment the wave was created. When two black holes collide, the final moments of their orbit contain the purest gravitational tones the universe can produce. These tones reveal the mass and spin of the black holes, the speed of their merger, and the shape of the space-time well created by their union. Listening to these tones is like hearing the voice of gravity itself, speaking in a language that light cannot translate. But black holes are not the only sources of gravitational waves. Neutron stars, with their intense densities and rapid orbits, also create waves that ripple outward. These waves carry details about the internal structure of the stars, how stiff or flexible they are, and how matter behaves when crushed into a state where its atoms are stripped apart. When two neutron stars collide, the wave carries the story of their spiraling descent, while the burst of light that follows reveals the explosion of matter flung outward from the collision. Together, the gravitational wave and the light create a single narrative, showing that general relativity and nuclear physics intertwine at the edge of extreme gravity. Textures of space-time reveal themselves in even subtler ways. Consider a spinning neutron star with a slight irregularity in its crust. As it rotates, that small imperfection generates steady, faint gravitational waves. These waves are quiet compared to the roars of black hole mergers, yet they carry precise information about the star's rotation. Detecting them requires immense sensitivity, but their presence would tell scientists how matter behaves under pressures and densities that no laboratory can replicate. Each neutron star becomes a lighthouse sending out a gravitational beam, its rhythm shaped by the geometry of space-time surrounding it. Even the fabric of the galaxy contributes to this cosmic symphony. Interactions between clusters, the motions of supermassive black holes, and the slow merging of distant galaxies all produce gravitational waves. These waves arrive with periods that stretch across years or even decades. They are felt not by laser detectors, but by the steady ticking of pulsars scattered across the galaxy. Pulsars act like cosmic clocks, their radio pulses arriving with extraordinary regularity. When a gravitational wave passes through the region of space between Earth and a pulsar, It changes the distance ever so slightly, shifting the arrival time of the pulses. By monitoring many pulsars across the sky, scientists can map waves that are too slow and too vast for ground-based detectors. This method forms a kind of galactic observatory, one that listens to space-time as it changes on scales far larger than any human-made structure. Each of these methods, from detectors on Earth to pulsars across the galaxy, reveals the same truth. Gravitational waves exist. They behave exactly as general relativity predicts. They confirm that mass in motion creates ripples in space-time, and that these ripples travel at the speed of light. The match between theory and observation runs deep, covering not only the existence of the waves, but their detailed patterns. Their frequency, their amplitude, their fading tone after a merger, all align with the geometry Einstein described. Yet the full implication of these waves reaches far beyond their detection. They offer a new way to explore the universe. Light reveals surfaces. It reveals heat, gas, dust, and energy. But gravitational waves reveal motion, structure, and mass in their purest form. They carry the story of the universe as written in curvature rather than brightness. They show that space-time is dynamic, reactive, alive with motion, even in the darkest voids. And as you listen more closely, you begin to sense that these waves may one day reveal something deeper still. They may carry clues about the limits of general relativity, clues about how space-time behaves when stretched to its breaking point, clues about where Einstein's description must give way to a new understanding. Now the universe feels less like a distant spectacle and more like a living structure that hums with motion. You have followed gravitational waves from black hole collisions to neutron star spirals, and from pulsars ticking across the galaxy to detectors on Earth that sense distortions smaller than anything the human body could ever feel. Yet the story of gravitational waves reaches even deeper, for these ripples do more than confirm Einstein's theory. They reveal how the universe changes, how it evolves, and how gravity behaves in regimes that no telescope of the past could ever reach. Imagine, for a moment, drifting through the quiet darkness between galaxies. There is no sound. There is no breeze. There is nothing but the scattered shimmer of distant stars. Yet beneath this silence, space-time breathes. Every few moments, a ripple stretches across the cosmic ocean, a wave born from some ancient collision billions of years away. These waves pass through you, through every atom of your body, through the vast emptiness of intergalactic space, through the fabric of the universe itself. They leave no visible trace, yet they carry the memory of their origin. Each wave is a messenger bringing news of events too distant, too obscured, or too violent for light alone to reveal. On Earth, the detectors that listen for these waves must remain almost impossibly still. They sit in long vacuum tunnels where laser beams bounce back and forth across distances measured with exquisite precision. When a gravitational wave passes, the beams shift ever so slightly. The length of one arm grows while the other shrinks, a silent tug and release in the geometry of space-time. The shift is tiny, far smaller than the width of a proton, yet it is enough to record the passing of a wave that began its journey long before life existed on Earth. These measurements require such sensitivity that even the faintest tremor in the ground, or the passing of a distant truck, or the movement of air inside the tunnels can disrupt the signal. Engineers have learned to silence these earthly noises so the universe itself can speak. Each detection carries a detailed signature. The waves begin softly, rising in frequency as the orbiting objects draw nearer. They reach a peak in the moment of collision, then fade quickly as the newly formed black hole settles into its final shape. The pattern of this fading, the way the wave quiets after the merger, reveals the curvature of space-time around the final object. Scientists can read this pattern like a fingerprint, allowing them to determine the mass, the spin, and the stability of the black hole. It is a form of observation so precise that even the tiniest deviation from Einstein's predictions would be noticeable. Yet every signal aligns with the theory, reinforcing its accuracy again and again. One of the most remarkable discoveries came when detectors recorded the collision of two neutron stars. Unlike black hole mergers, these events produce not only gravitational waves, but a burst of electromagnetic radiation. Within seconds of the first wave arriving at Earth, telescopes around the world turned toward the source. They saw a flash of light, followed by a long, fading glow. This combination revealed that the merger had produced heavy elements, confirming theories about how gold, platinum, and other dense materials form in the universe. The gravitational wave provided the timing and the motion. The light provided the chemistry and the energy. Together, they told a story far richer than either signal alone could reveal. Gravitational waves also offer a way to explore regions that light cannot reach. When black holes merge, no light escapes the final moment before collision. The event horizon swallows everything, yet the gravitational wave carries the imprint of that moment with perfect clarity. It brings information from inside regions where no photon could ever travel. It allows scientists to observe processes hidden behind layers of matter, behind clouds of gas, or behind the very boundaries of spacetime. This ability transforms gravitational waves into a new kind of sense, one that complements vision by granting access to the deepest shadows of the cosmos. Beyond these dramatic events, there exists an entire background of gravitational waves filling the universe. These waves come from countless sources, some so distant that they blur together into a steady hum. Pulsar timing arrays have begun to detect this long wavelength background, stretching across years rather than seconds. This slow rhythm reveals the behavior of supermassive black holes orbiting one another in the hearts of merging galaxies. It shows how entire galactic structures evolve over time, providing insight into processes that unfold on scales far beyond human lifetimes. As you reach the final moments of this chapter, a new truth becomes clear. Gravitational waves do more than confirm that gravity is geometry. They reveal that space-time is not static. It moves. It vibrates. It responds to motion with elegance and precision. Every wave recorded on Earth is a direct demonstration that gravity is not a force reaching across the void. It is the shape of the void itself, stretching and flexing in response to mass and energy. Yet even this remarkable success does not complete the story of general relativity. For as accurate as the theory remains, it encounters boundaries in places where gravity becomes overwhelming or where the smallest scales of nature come into play. The universe now points toward a deeper challenge, one that general relativity alone cannot answer. To follow that challenge, you must journey to the edges of Einstein's theory, where space-time bends toward the unknown. There comes a moment in every great theory when the universe reveals the edges of its map, the quiet regions where the equations begin to strain and the clarity of understanding gives way to a soft, deliberate uncertainty. General relativity, one of the most successful scientific achievements in history, reaches such a moment not with contradiction, but with honesty. It describes gravity as curved space-time with astonishing precision, matching experiments across planets, stars, galaxies, and even the ripples of gravitational waves traveling for billions of years. And yet, when you follow this curvature into the most extreme environments the universe contains, the elegant geometry begins to falter. The fault is not in the theory. The fault is in the universe for being even deeper than the equations that describe it. Imagine descending once again toward the center of a black hole. At first, the geometry behaves exactly as general relativity predicts. Space-time bends inward, light curves sharply, every path falls toward the center. But as you continue deeper, the curvature steepens until the equations predict an infinite value, a point where density and space-time curvature grow without bound. This singularity is not a physical location. It is the moment when general relativity can no longer describe the environment accurately. It is a boundary, a marker that says the universe has reached scales where quantum effects become unavoidable. Quantum mechanics does not allow infinities. It demands that uncertainty governs the smallest distances, that fields fluctuate restlessly, that nothing can collapse into a perfect point. And in this clash, you see the first clear sign that general relativity is incomplete. Turn now toward the earliest moments of the universe. As you travel back through cosmic history, galaxies draw closer, temperatures rise, and densities increase. General relativity describes this evolution beautifully until the universe becomes so small and so dense that the equations predict another singularity. Once again, the prediction does not describe a literal point of infinite compression. It describes the failure of the classical theory at scales where quantum fluctuations must dominate. The early universe becomes another boundary where space and time grow so energetic and so tightly compressed that the smooth geometry assumed by general relativity breaks down. These boundaries reveal the same underlying truth. General relativity assumes that spacetime is continuous, smooth, and well-defined at every scale. Quantum mechanics insists that the smallest scales are uncertain, fluctuating, restless. These two visions of reality cannot remain separate forever. They must eventually overlap, and when they do, the theories begin to conflict. This conflict does not weaken either theory. It reveals that each describes only part of a deeper framework that has not yet been discovered. To appreciate this tension, imagine shrinking yourself down to distances far smaller than any particle accelerator has ever reached. At these scales, quantum fluctuations grow stronger and stronger. Energies rise sharply. Time itself jitters. The geometry that general relativity depends on loses its meaning. A curve can no longer remain smooth if the surface it rests upon flickers unpredictably. And a field cannot behave continuously when the quantum rules demand that everything, including spacetime itself, must fluctuate. The Planck scale, an unimaginably tiny distance, many trillions of times smaller than a proton, becomes the region where the classical picture dissolves entirely. General relativity cannot operate here. It cannot ignore the quantum storm. Black hole interiors offer a similar challenge from a different direction. Even before reaching the singularity predicted by general relativity, you encounter curvatures so extreme that quantum effects must alter the classical description. The horizon hides the deepest region, yet the mathematics reveal that something must intervene before infinite curvature can form. Quantum principles demand it. The classical theory cannot provide it. This is another boundary, another signpost pointing toward a more complete understanding. The tension grows sharper when you consider the information paradox. According to classical general relativity, any object crossing the event horizon is forever hidden from the outside universe. According to quantum mechanics, information about physical states cannot be destroyed. These two principles collide at the edge of a black hole, revealing a contradiction that cannot be resolved within either framework alone. The paradox is not a flaw in observations. It is a signal that a deeper theory must unify the rules governing geometry and the rules governing information. Dark energy provides yet another boundary, though in a gentler form. Observations show that the expansion of the universe is accelerating. General relativity accommodates this acceleration through a term in its equations, but the nature of this energy remains unknown. It behaves like a property of spacetime itself, influencing geometry on the largest scales. Yet no known quantum field explains its origin. The presence of dark energy hints that spacetime contains features not yet understood, features that may require quantum gravity to decode. Even gravitational waves reveal the boundary indirectly. The waves we have detected behave exactly as general relativity predicts. But waves at extremely high energies, such as those produced in the first moments after the universe began, would push the theory into regions where quantum corrections become significant. The fact that we have not yet detected such waves does not mean they do not exist. It simply means our detectors are not yet sensitive enough to hear them. The earliest gravitational waves may carry imprints of quantum spacetime, waiting quietly for future instruments to reveal them. And so, every boundary tells the same story. General relativity is complete within its realm, but its realm has limits. These limits do not diminish the theory, they elevate it. They show exactly where the next questions lie and where the next answers must emerge. A mature theory does not pretend to describe everything. It explains what it can and reveals where it cannot. Einstein's geometry has done this with remarkable clarity. It has drawn the map of the universe from planets to galaxies, from stars to black holes, from local time dilation to cosmic expansion. And at the edges of this map, it has outlined the frontier of quantum gravity. Standing here, at these boundaries, you feel the universe calling forward. The singularities at the center of black holes and at the beginning of cosmic expansion are not failures. They are invitations. The Planck scale is not the end of physics. It is the place where a deeper layer awaits discovery. The information paradox is not a contradiction. It is a clue. And the unknown nature of dark energy is not a gap. It is a horizon. General relativity remains one of the most accurate, elegant, and powerful theories ever created. It does not collapse at its boundaries. It simply steps aside, pointing toward the next chapter of understanding. And in that gesture, it reveals that the universe is not only stranger than we once believed. It is richer, deeper, and more layered than any single theory can describe alone. The search for quantum gravity begins like a traveler standing at the meeting point of two worlds, each governed by rules that work flawlessly on their own, yet refuse to blend into a single picture. On one side lies the vast, smooth geometry of general relativity, where planets glide along curves in spacetime and black holes form from the collapse of massive stars. On the other side lies the quantum world, a place where particles do not move in straight lines but in probabilities, where fields flicker with restless energy, and where uncertainty is woven into the fabric of every interaction. Each world has been tested with exquisite precision. Each world matches experiments perfectly. Yet when you try to look at the universe through both lenses at once, the image fractures. And in that fracture, physics encounters one of the greatest puzzles ever faced. Imagine again the interior of a black hole, the place where general relativity predicts a singularity, a region where curvature rises without limit. Quantum mechanics does not allow infinities. It demands that physical quantities remain finite, uncertain, fluctuating, but never divergent. The clash is not philosophical, but mathematical. It tells you that the equations of general relativity, beautiful as they are, do not describe the smallest scales of nature. Something deeper must exist beneath the smooth curves. Something that prevents space-time from collapsing into a point. Something that unites geometry with quantum rules. Now turn toward the earliest moments of the universe. As you follow the expansion backward, the temperature and density grow rapidly. The universe becomes smaller, hotter, and more compressed until the equations of general relativity reach a point where they fail. Not because they are wrong, but because they are incomplete. At scales this small, quantum fluctuations of space-time become too large to ignore. The classical geometry dissolves, and once again, the universe demands a theory that blends gravity and quantum mechanics into one framework. Physicists have spent decades searching for such a theory. Loop quantum gravity imagines that area and volume come in tiny discrete units, woven into networks that create space itself. In this view, the smoothness we see every day is the large-scale result of countless microscopic loops. This idea naturally eliminates singularities, replacing them with transitions where space-time structure prevents infinite curvature. Nothing in this framework violates known physics, yet it remains unconfirmed because the scales at which these effects occur lie far beyond direct experimentation. String theory offers a very different vision. It proposes that the universe is not made of point-like particles, but of tiny vibrating strings. Each vibration mode corresponds to a distinct particle, and gravity emerges naturally as one of the vibration states. The theory requires additional spatial dimensions, curled into shapes far too small to detect with current technology. It is mathematically rich, enormously powerful, and capable of unifying the forces of nature, yet still awaits experimental evidence. It remains a map of what might be possible, rather than a confirmed description of what is. Other approaches, such as causal dynamical triangulations, attempt to build spacetime from small geometric tiles that assemble themselves into larger structures. By simulating how these tiles behave under quantum rules, physicists hope to see a smooth spacetime emerge from discrete pieces. Early results are encouraging, yet not complete. The theory can reproduce aspects of four-dimensional spacetime, but much remains unknown, especially under conditions of extreme curvature. Experiments attempting to probe quantum gravity face enormous challenges. Gravity is incredibly weak compared to other forces, so its quantum effects are subtle, buried beneath layers of classical behavior. Physicists attempt to place small masses into delicate superposition states, hoping to see whether gravity can entangle them. If it can, gravity must be a quantum force. If it cannot, then gravity may be fundamentally different from all other interactions. These experiments push technology to its limits, requiring stability and precision. Few laboratories can achieve, yet the progress continues. Astronomy offers its own path. Gravitational waves recorded from black hole mergers are analyzed for small deviations from classical predictions. The final tones of these waves, the quiet ringing of spacetime after the merger, might someday reveal hints of quantum corrections. Pulsar timing arrays search for slow gravitational waves stretched across years, looking for distortions that might reveal new physics. The cosmic microwave background carries faint patterns that may reflect quantum fluctuations from the earliest universe. These clues are subtle, requiring instruments even more sensitive than those available today. Perhaps the most profound clue lies in the information paradox. Quantum mechanics insists that information cannot be destroyed. General relativity predicts that anything falling into a black hole becomes unreachable beyond the event horizon. These two statements cannot both be fully correct. Resolving this paradox is not optional. Any theory of quantum gravity must explain how information is preserved in a universe where spacetime can fold itself into horizons. This requirement shapes every candidate theory, forcing it to align with the core principles of both quantum physics and geometry. Through all these avenues, the search remains grounded in evidence. Physicists do not accept speculation as truth. They build theories that respect the known laws of nature, test their predictions, and wait for the universe to reveal the next clue. No theory has yet succeeded fully. No experiment has yet detected direct quantum gravitational effects. But the search continues with patience, rigor, and humility. It does not seek to replace general relativity. It seeks to complete it, to reveal the deeper structure beneath the geometry of spacetime. And now, with the boundaries of general relativity illuminated and the quest for quantum gravity laid before you, the journey turns toward its final realization. The universe has spoken through light, matter, motion, and waves. It has revealed the truth piece by piece. And as you step into the final chapter, that truth becomes whole. Everything you have learned, everything the universe has shown through measurement and observation, now converges into a single, unified understanding. Gravity, once thought to be an invisible pull, is not a force at all. It is the shape of spacetime. This is not metaphor. This is not interpretation. It is the conclusion drawn from more than 100 years of evidence, confirmed through experiments that span the smallest measurements of time to the largest structures in the cosmos. Imagine floating freely above the Earth, weightless, drifting along a path that feels effortless. You are not escaping gravity. You are following the natural motion defined by space-time itself. Your body traces a geodesic, the straightest possible path in a curved geometry. The sensation of falling is the sensation of motion in curved space-time. The sensation of weight is the sensation of resisting that motion. When you stand on the ground, the earth pushes upward against you, preventing you from following your natural path. In this picture, gravity becomes the quiet architect of motion. It does not pull, it shapes. The evidence for this idea is overwhelming. Clocks placed at different heights measure different flows of time. Light bends around massive bodies, tracing the curves of space-time. Planets follow orbits that match the exact geometry predicted by general relativity. Gravitational waves ripple outward when massive objects collide, stretching and compressing space-time in ways recorded directly by detectors on Earth. Black holes cast shadows that match the shapes predicted by Einstein's equations. The expansion of the universe follows patterns defined by the curvature of cosmic space-time. Each observation stands independently, yet everyone supports the same principle. This clarity transforms the universe. The orbit of the moon becomes a path shaped by geometry. The tides become a response to the curvature created by the moon's mass. The slow drift of Mercury becomes a consequence of the deeper curvature near the sun. The timing signals from satellites become a demonstration that time itself flows differently depending on the gravitational field. Even your own life unfolds through a space-time whose rhythm is shaped by the matter beneath your feet. General relativity does all this with elegance. It requires no hidden mechanisms. It needs only the recognition that space-time bends where mass and energy reside. And where space-time bends, motion changes. This idea reduces to Newton's laws when gravity is weak, preserving every classical success. But it extends far beyond them, revealing phenomena the classical picture never could. Black holes, gravitational waves, time dilation, and the expansion of space itself. Yet the deepest beauty of general relativity lies not just in its power, but in its humility. It does not claim to describe the quantum world. It does not pretend to resolve the earliest instant of the universe or the interior of singularities. Instead, it points directly to these boundaries, showing exactly where the next understanding must emerge. It reveals the edges of its domain without denying its validity. It stands complete within the world it describes and honest about the world it cannot reach. And this honesty brings the story to its ending. The universe is not held together by invisible pulls. It is shaped by curvature. Space and time are not rigid. They are dynamic, flexible, and intertwined. Matter shapes space-time. Space-time shapes motion. Every orbit, every fall, every ripple, every flow of time emerges from this relationship. Gravity is geometry. Geometry is gravity. And the illusion was never that gravity existed. The illusion was the belief that space and time were passive. Now the illusion is gone. The truth remains. Curvature, not force, governs the universe.